An active filter is a type of analog electronic filter that uses active components such as an amplifier. An amplifier prevents the load impedance of the following stage from affecting the characteristics of the filter. An active filter can have complex poles and zeros without using a bulky or expensive inductor. The shape of the response, the Q, and the tuned frequency can often be set with inexpensive variable resistors. In some active filter circuits, one parameter can be adjusted without affecting the others. Using active elements has some limitations. Basic filter design equations neglect the finite bandwidth of amplifiers. Available active devices have limited bandwidth, so they are often impractical at high frequencies. Amplifiers consume power and inject noise into a system. Certain circuit topologies may be impractical if no DC path is provided for bias current to the amplifier elements. Power handling capability is limited by the amplifier stages. Active filter circuit configurations include Sallen-Key and VCVS filters, state variable filters and biquadratic or biquad filters, dual amplifier band pass, Wien-Notch, multiple feedback filters, flyage, Ackerberg-Mossberg. Active filters can implement the same transfer functions as passive filters. Common transfer functions are high-pass filter, attenuation of frequencies below their cutoff points, low-pass filter, attenuation of frequencies above their cutoff points, band-pass filter, attenuation of frequencies both above and below those they allow to pass, notch filter, attenuation of certain frequencies while allowing all others to pass. Combinations are possible, such as notch and high-pass. Another example is an elliptic filter. Design of active filters. To design filters, the specifications that need to be established include the range of desired frequencies together with the shape of the frequency response. This indicates the variety of filter and the center or corner frequencies. Input and output impedance requirements. These limit the circuit topologies available. For example, most, but not all active filter topologies provide a buffered output. However, remember that the internal output impedance of operational amplifiers, if used, may rise markedly at high frequencies and reduce the attenuation from that expected. Be aware that some high-pass filter topologies present the input with almost a short circuit to high frequencies. Dynamic range of the active elements. The amplifier should not saturate at expected input signals, nor should it be operated at such low amplitudes that noise dominates. The degree to which unwanted signals should be rejected. In the case of narrowband band-pass filters, the Q determines the -3 dB bandwidth but also the degree of rejection of frequencies far removed from the center frequency. If these two requirements are in conflict, then a staggered tuning band-pass filter may be needed. For notch filters, the degree to which unwanted signals at the notch frequency must be rejected determines the accuracy of the components, but not the Q, which is governed by desired steepness of the notch, i.e., the bandwidth around the notch before attenuation becomes small. For high-pass and low-pass, the required rejection may determine the slope of attenuation needed, and thus the order of the filter. A second-order all-pole filter gives an ultimate slope of about 12 dB per octave, but the slope close to the corner frequency is much less, sometimes necessitating a notch be added to the filter. The allowable ripple within the pass band of high-pass and low-pass filters, along with the shape of the frequency response curve near the corner frequency, determine the damping ratio or damping factor. This also affects the phase response, and the time response to a square wave input. Several important response shapes have well-known names. Chebyshev filter, peaking, ripple in the passband before the corner, Q greater than 0.7071 for second-order filters. Butterworth filter, maximally flat amplitude, response, Q equals 0.7071 for second-order filters. Linkwitz-Riley filter, desirable properties for audio crossover applications. Fastest rise time with no overshoot, QE equals 0.5 painter or transitional Thomson-Butterworth or compromise filter, faster fall off than Bessel, QE equals 0.639 for second order filters, Bessel filter, maximally flat group delay, QE equals 0.577 for second order filters, elliptic filter or Cower filter, add a notch just outside the passband, to give a much greater slope in this region than the combination of order and damping ratio without the notch.